and they are going to very quickly show you what we mean by coordinated trajectories, talk to you a little bit about how it works, the fantastic work they've done for us, and then treat you to something really special that we've just gotten working here in the lab in the last week or so we're very excited about that. And I'll hand it over to Bilal.
Hello everyone. So as Jeanette introduced, my name is Bilal Mehdi, and I've been working here with Javier, who you see at the back right now. And we have been working with PIs, Dr. Ana Trujillo and Dr. Dina Allen. So what we did here is basically coordinated flight with multiple vehicles. And I'm gonna, so to introduce what that means, we are basically gonna start off with a particular demo. So to start off with demo, I'll first explain what are we trying to achieve here. Scientists or atmospheric scientists are often interested in correlative data. What that basically means is that they could have a vehicle collecting data at point A, and at this very same time, they would want a different vehicle B collecting maybe a different data at a different point B, right? And these point A and point B could be moving, so you would want maybe the vehicles to follow a certain trajectory. So often what they do right now is they would have a sensor, maybe something like this. But what they do is they just put it on a hot air balloon or something and they drop it. And it keeps reading, it basically transmits reading while it's falling down, so you can see the actual sensor sitting inside this box. Or they can have a different sensor, maybe a smaller one that looks like this, which basically does the same thing. But if you're just dropping them, you cannot really control where they're going. So to actually have correlative data, what you need is a controlled flight. And not only that, you need multiple vehicles doing a coordinated flight, right? So we're going to demonstrate a small scale version of that right now, where we have 4 different vehicles sitting here, and what they're going to do is basically they'll fly in a circle. This is something that scientists are often interested in, following some sort of helical or circular motion. So once they're ready, we're going to take off and show you how they do it. So
we're connected. Control for initialize. Taking off. 3, 2, 1. Take off.
So what we see happening right now is that these vehicles are taken off and now they're following a circular path. And what's happening is that this is all autonomous. Nobody is piloting them. They are doing this prop, and in an actual mission they would be collecting data in a coordinated manner because they're all keeping a certain, for example, phase degree from each other, a certain distance from each other. And they follow this in a coordinated way. If one of them is slow or faster than the other one would respond divided the mission in six. And as I mentioned before, everything is autonomous here. So the human only comes in for starting the mission and ending the mission. So once they're done, what Javier is going to do is have them to land, and now they're done. Okay. So that was a demonstration of, yeah, and also on the screen, if you notice, you could see where they're moving because they were all, these vehicles have these icon balls in there, so we can see where they're going so that we can control how they perform the mission. So that was the feedback that our algorithm uses to control them. Okay, so that was the demonstration. But if you noticed, the title has something else in there. We said coordinated flight with heterogeneous vehicles. I didn't show heterogeneous vehicles right now. They were all the same. Why do we need heterogeneous vehicles? Well, I also showed you 2 different sensors. Different sensors often have different requirements. One could be small, one could be big. And this could often mean a different type of vehicle. If the sensor is too big, maybe these small quads are not good enough. Or if the sensor is too small, maybe you can go for even a smaller vehicle. So what we wanted to achieve here is develop a system where you could have different types of vehicle following a coordinated mission. So I'll start on the presentation for that. All right. So now coming to the presentation. I'll go over the introduction, explain what I'm doing. We had a little bit of demo, but I'll go over it in a bit more detail in the introduction. I'll introduce the platforms that we are using. You've already seen some of them flying, there would be more, and I'll introduce them. After that, Javier is going to explain or go over the algorithms that we have been implementing on these vehicles, ending with a conclusion and another demo. Now, this demo is going to be the heterogeneous one, the ultimate goal that we have been trying to do here. All right. So, okay, so we saw a demo, and I tried to explain an application for it, but there are a lot more, right? So, for example, one thing that the Autonomy Incubator is interested in is package delivery, that basically need coordinated flight. Why does it need it? Think about having one interest point for multiple vehicles. You could have multiple packages coming in. Now, you wouldn't want those vehicles to bump into each other trying to deliver at the same time. You would want them to coordinate. So that's an application for coordinated flight right there. There could be coordination between several means of transport. So, for example, a ship is coming to a certain dock, and a truck has to take a certain package from there. They need to coordinate between each other. There could be moving platforms. So, for example, on this figure over here, let's see if it works. It's not really visible.
Check to make sure it's on.
Yeah, it's on. Okay. So here you see a few helicopters coordinating with a ship. And there could be other operations such as search and rescue, reconnaissance, etc. Another interesting application is, for example, if you have a satellite which is collecting some data and you want to calibrate the satellite, what you need to do is collect the same data from the satellite and from a different sensor, for example, that could be attached to a vehicle. So what you would want is these two things to coordinate, or basically the airplane to coordinate with the satellite so they read the exact same data at the same time. So that's another application for coordinated flight. So those are the bigger goals, but in 2 months, we couldn't do all of it. So we had some small goals to achieve here. We were trying to do small-scale versions of coordinated flights with heterogeneous vehicles, and whenever we were doing anything for implementation, we first needed to do the sanity checks. So, for example, we needed to test the algorithm that we were doing in simulation first. So we had a simulation environment developed for small vehicles such as quadrotors, where we could test them out in computer before going to actual flight test, because that can often lead to safety problems if you're trying an untested algorithm on an actual vehicle. And we do some other small-scale tests before moving on to the actual one. We first did homogeneous flight, so we'd have like the one that we just saw, where we had the same vehicles following a certain coordinated trajectory, but ultimately we moved on to the multiple heterogeneous one. But that wasn't all. We also had some other parallel efforts going on. So we embedded safety features for autonomous flight. Since we are testing them almost every day, multiple times, we wouldn't want any safety hazards in there. So, for example, we had Nick discussed some of the safety measures that we can embed in vehicles. So we had a smaller implementation of those kind of safety measures for these vehicles. And then we also did some more research in trajectory generation and collision avoidance. For trajectory generation, one of the goals that we did was that when we are defining the trajectories, for example, the circles that the vehicles that just followed, we want the scientists to be able to easily tell the vehicles what to do. So we integrated our trajectory generation with gesture recognition with Megan, who's standing right there. She helped us with that. And then we did other things such as supporting the Autonomy Incubator for demos. But so what we did in the summer also fits in with some other goals that we are following back in the University of Illinois for the coordinated flight algorithms that we are developing. So over there, in this broader goal, the work methodology that we follow is that we have a certain theory for a certain algorithm that it should work or not. We test it through simulation, go to a flight in structured environment and in structured environments, with an eventual goal of flight in an unstructured environment. In parallel, what we also try to do is, for these algorithms, we try to develop formal mathematical proofs showing that they will work under some practical assumptions. And the eventual goal is that once we have this and this, we can have them certified so that they could be used in all commercial UAVs or UAS out there. So what we have done here in the summer is basically these parts. We had some theory and we did some simulation and some flight in the structured environments as the one that we just showed. All right, so now just a brief description of the platforms that we're using. We just saw air drones flying, so we have, for example, one sitting here. This is very similar to the one that we just flew. We use them because they're easy to fly. They come with a lot of embedded features in them. So for example, takeoff, landing, and hovering are already embedded in them, so we don't need to do anything about them. We just need to command them to do it, and their onboard software will do it for us. So they're good for testing out different things because they're easy to start off. So for them, we implemented other outer loop implementations, such as the path following that we just saw, that we wanted them to follow a circle, and they did. Other than that, we embedded some safety features. So if they lose communication, if they're going out of icon range, etc., they have certain maneuvers to either land or start hovering in those conditions. And then we had some hardware modifications. So you see these nice NASA logo on them. So all the Autonomy Incubator team helped us with that. The intern spent quite a lot of time trying to get them on. And then we also had to, of course, attach icon markers for the icon flight. The other vehicle is the Crazy Fly, sitting right here. The reason that we are interested in them is that, first of all, they're different from air drones. So when we are doing heterogeneous flight, it's necessary to have a different one. And they're good because they're smaller, so we can fit a lot of them in a very small range. So in the long run, we could have maybe hundreds of them flying right here. And also, they have some nice properties that they can still, although they're small, but they can still support a small payload. For these, we had to implement a few things. Unlike air drones, they don't have their own takeoff and land modes implemented, so we had to do that. And other than that, we had to embed safety features just as air drones for them. We printed the 3D frames with the help of the interns here, so that we can attach icon balls to them and they can actually fly. But I'd like to point out that those are not the only difference between the vehicles. Air drones, when they take in commands, their software takes in translational velocities in X, Y, and Z axes. These things the commands that they take in is translation velocity in the height, but in the X and Y axes, they basically, we need to command roll and pitch angle. So this is different from what air drone does. But through DDS, we were able to communicate with them in a very similar way. And with a small modification, we had our control modified for these vehicles. And after that slight modification, it fits in, and we could do heterogeneous flight. So now I'll ask Javier to continue and explain the algorithms that we use.
Hi everyone, thank you for coming. So I'm Javier, a PhD student from the University of Illinois, and today I'll talk about the algorithms that we have designed, tested, and implemented in the Autonomy Incubator to achieve this coordinated flight with heterogeneous vehicles. So this is the control architecture that is running right now on that computer, and it can be broken down into three simple algorithms, which are trajectory generation, path following, and time coordination. But before I go over them, I want you to think of an actual mission, like package delivery. The first thing you want to do is plan your mission, and this is where our trajectory generation algorithm takes part in. So first, we generate trajectories. Then once we have the mission plan and the trajectory generated, we want to execute the mission. So what we do is we have to make the vehicles converge to their paths and follow them. So that's taken care by the path following algorithm. And the last part, since we are dealing with time-critical systems that need coordination, we need to adjust their velocities along their paths so that they coordinate. And that's where the time-critical coordination algorithm takes place. This bigger block is what eventually will be implemented in a single vehicle. And as you can see, that vehicle communicates over a network with the other vehicles. They are self-aware of each other. I have to thank Gil for all the help on developing a vehicle-agnostic communication protocol. And now I'll move on to each of the individual algorithms. First of all, the trajectory generation. We want to plan our mission, and there's different approaches to this. One of the approaches that we've been working this summer is developing a library of trajectories for gesture recognition. This was particularly tailored for the atmospheric science mission, where we expect to have non-UAV experts flying these vehicles. So we developed a library of trajectories that will be the building blocks of much complicated trajectories that the scientists will define with gestures. For that, we're using Bezier curves for several nice properties, geometrical properties, and several available algorithms with very nice features. And this is one example of a trajectory that we developed. And on this video, you can see our intern, Lauren, using the gesture interface and defining a trajectory. So the video is sped up, and this is the final result, basically a square and a spiral. Another approach will be autonomously generating the trajectories. So if you have, say, 100 vehicles and you want to autonomously generate trajectories, it won't be feasible for a single operator to define them. So what we do is we generate them autonomously. For that, we use an optimization function and a type of curves that have, again, very nice properties. It's easy to compute the distance among the trajectories. And we also impose several constraints, like a safety inter-vehicle distance constraint, or dynamic constraints of the vehicle, like maximum and minimum acceleration, maximum and minimum turning rates. And this is one of the examples that we developed last year. Here, I think we had 7 UAVs, and we designed trajectories so all the UAVs exchange position in this manner. So once we have our trajectories, once we have our mission defined, we have to execute the mission. We make the vehicles converge to their trajectories and follow their paths. As Bilal mentioned, one of the focuses of our research is proving that the algorithms will behave as expected. So we have proven that the algorithm will converge exponentially to the desired behavior with a guaranteed rate of convergence. The path-following algorithm, there's 2 implementations to the path-following algorithm. One is for multi-rotors, the other one is for fixed-wing. The philosophy behind the algorithm is the same, but the actual implementation is very different. So for both fixed-wing and multi-rotors, what we want is to align the UAV with a curve and make the velocity vector of each UAV align and follow a point along their desired path. That's how we do path following. However, for the multi-rotor, we use thrust, pitch, and roll rates. And for the fixed wing, we use pitch and yaw. So it's slightly different. And the last part of our algorithms, the last piece of our algorithms is time-critical coordination. I want to emphasize that this is completely vehicle agnostic. It's the same algorithm for every kind of vehicle: a satellite, a car, a multi-rotor, a fixed wing, is exactly the same algorithm for everyone, and we can impose different kinds of constraints. Relative temporal constraints, that means the vehicles will arrive to their final destination according to a predefined inter-vehicle schedule. So as long as they arrive according to that schedule, it's okay. It doesn't really matter when they arrive. Then we have relaxed absolute temporal constraints. So the vehicles are tasked to arrive to their destinations within a temporal window. And then we have strict absolute temporal constraints. So the vehicles must arrive to their final destination at a specific time, at a specific moment. Okay? So we have several algorithms developed for this. Some of them have leader-follower hierarchy, and some of them don't have any kind of hierarchy. So this is an example of the algorithm. As you can see, this is for leaders and followers. I won't go over it, but I just wanted to show more or less how the equations look like. And Bilal has emphasized our methodology. The first part was simulation. So here's a simulation result of an air auto landing scenario with 5 vehicles. All the vehicles have started with an initial offset in attitude and position with respect to their assigned trajectories. The path following algorithm makes the vehicles converge to the paths, and the time critical coordination algorithm makes the vehicles arrive to the landing strip at a specific time. And the video on the right, once we validated our algorithms with theory and simulation, the video on the right is me playing with these drones, and basically that drone that I have here is fighting with me. I'm trying to make it move faster or slower. At the beginning it was slower, and now it's a bit faster that the vehicle had planned to. And the other vehicles are aware of the pace of this vehicle and correct their trajectories to guarantee a safety inter-vehicle distance. So to conclude, we've integrated our trajectory generation with Megan gesture recognition algorithm. Thank you very much, Megan. We've developed a simulation environment with a quaternion-based rigid body dynamics for algorithms. That was for our simulation part. And we've achieved a coordinated flight of heterogeneous vehicles. Once again, I want to emphasize that our algorithms are vehicle agnostic, so we have been able to integrate this crazy flight in 1 week in our system. Of course, AON and the DDS framework played a major role in that fast, rapid prototyping and development. So, future work. We do a lot of research towards autonomy. So some of the things that we're interested in are management of priority queues for loitering aircraft, the ab initio problem, collision avoidance for multiple cooperating vehicles, and of course the formal proofs of our algorithms. So this goes along the lines of the next generation air transportation system, or at least it's interesting. And one thing that we came up this summer is the Microsoft HoloLens proposal. So we're trying to develop an immersive gesture-based interface with holographic feedback for non-UV experts to define their trajectories in a more natural way. And that would be a collaboration between the Autonomy Incubator, CMU, and UIUC. So without further ado, if everything's ready, we can begin the...
Can you hold 1 second? Sure. And let Abby get behind the... You got some? Behind that.
So what we're gonna show you next is the heterogeneous coordinated flight demo. And as you can see, we have 2 bigger vehicles, which are the air drones here, and 2 smaller vehicles, which are the crazy flies. And if you guys are ready, feel free to take off.
Yeah. Taking off in 3, 2, 1, take off. taking fast forward.
Right now, we have autonomous control. The vehicles are self-aware of each other. They're talking to each other continuously and making sure that their mission pace is as expected. The bigger vehicles will carry bigger sensors like the white box over here, and the smaller vehicles will carry lighter sensors like the Autonomy sensor on top of it. It's exactly the same mission that we've seen before, but with different vehicles. I want to emphasize again that we are running exactly the same code with different vehicles, so it's vehicle agnostic. So thank you very much. I hope you enjoyed the demo. I would like to acknowledge all the members of the Autonomy Incubator. Great work this summer. Also, special thanks to Danet, great mentor, for great support and great leadership. Ana Trujillo, thank you very much. We appreciate your insight in AIAA and this summer. And also Gil Montag, he's made our life much easier with the DDS implementation. Megan, we've worked very closely for the trajectory implementation with hand gestures. And Paul Rodhar, which is not here today. Also Steve Snyder, he's been very patient and he's been a loyal escort of Bilal and our advisor, Dr. Naira Habakim. Thank you very much.
Nice job.